Well, today I am going to explain the different charge distributions and their electric fields. So, first of all, we will consider regular distributions like a linear distribution. For example, some charge exists in a line like this. This is called a linear distribution of charge. One more, planar distribution, like the charge exists in planes, in a sheet of plane. So on the sheet, if we assume that a sheet is there, so every particle on the sheet is like a charge. So that is called a planar charge. So surface charge distributions we call it as. And volumetric cubical charge distributions, like for example, you have a charge like this. So assume that this is one plane of a cube and this is another plane, so that it seems to be a cubical charge, or cubical charge means volumetric charge distributions. For example, consider as a spherical charged body like a nucleus. A nucleus has total positive charge which is distributed in a spherical way. So that is volumetric charge distributions or cubical charge distributions we call it as. So these are the regular shaped charge distributions. So for this, how to calculate the fields around them or inside of that particles or the distributions and all. So first of all, we already know that if a single charge exists like this, around it you have a charge impact like electric field. So that field will be calculated in terms of R, like E is equal to K, that is 1 by 4 pi epsilon naught K into Q by R square. For example, if this is a charge Q, you are considering the field at a distance R from the charge, then the field intensity at that point is written as K into Q by R square. So this is for single charge. Okay, for example, if you have two charges, what is the field around it? We know that a dipole is a combination of two charges. So around it, the fields are calculated previously. You in your textbook also you have. So now, if you take three charges, taking superposition of fields, we can calculate the field around that three charges. If we take four charges, taking superposition of the field vectorially, you can calculate the field around that charges or inside that charges. But what happens if multiple charges exists there? A multiple charges like a linear charge, so many charges in a line. Here are surfacial charge distributions like a plane, in a plane, here so many charges are there. Like a cubical charge, volumetric charge distributions like nucleus. So here we can't apply superposition theorem. It's too difficult to calculate the field around it and inside it. So for that type of distributions, Gauss gave a law, distribution law, which is taken as the flux passing through a charge distribution is equal to the 1 by epsilon naught times that of the charge existed, total charge existed on the distribution. The flux passing through a charge distribution is equal to 1 by epsilon naught times that of the charge existed on that distribution. For example, you have a line of charge like this. For example, the total charge is Q, then the flux from that charge is equal to Q by epsilon naught. So that is the law given by the Gauss. So with this law, using this law, we now will find out the field around these charge distributions, regular charge distributions. So we already know that the flux passing through the flux passing through a charge is equal to the scalar product of the field of around that charge within a considered area S. For example, you have considered some area in a around a charge. So through that area, how much flux will flow is defines the field. For example, here you have a charge, around it the field exists. So you are considering a unit area here. So some flux will flow through it. So the flux that flux phi is equal to the field E into the area that you have considered for that flux calculation. So this is already we know from the previous concepts. So now we have two concepts, that is phi is equal to E dot ds, and according to Gauss, for a particular area, Gaussian surface we call it as, for a particular area around the charge, the flux passing through is equal to the charge by epsilon, 1 by epsilon naught times of the charge on it. So these two is needed for us to find the fields about different distribution of charges. So now I am using this basic class. Now I'll explain one by one, like linear charge distributions, surfacial charge distributions, and volumetric charge distributions. First of all, I am considering a linear charge distribution like this. So one by one the line charge exists in it. So but now we need to consider the field, how the field will be. If you take this one charge, so around the charge the field lines may be like this. So assume that this is like this also. But here also there is a similar charge, so it will the force line which is upwards will be cancelled out, and there is no field line here, and your all field lines will be graduated like this. So that means assume that you have a charge line, a line of charge here. So your field lines will be like this, like a brush with which we will wash some bottles. You know, in home, in some bottles we will wash with some brush. A brush has like this, a stem is there, around that stem you have bristles like this. So those are uniform and those are parallel to each other like this. So assume that the same type will be here. So here the field will be like this. So I am considering a unit Gaussian surface around this. So unit Gaussian surface means I am considering a imaginary cylindrical surface around this charge. Imaginary cylindrical surface around this charge whose radius is R, whose length is L. So here, first of all, this is a charge distribution. So what will be the charge on it? So for example, you have a charge Q on a hole. So what is the charge at unit length? Charge at unit length, because it is an infinite charge distributions. So here we need to consider the density of the charge density of the distribution. So for that charge density we call it as sigma, linear charge density. It is called sigma, which is called as linear charge density. That means you are considering a line of charge, so it is linear charge density. Sigma is equal to Q by this is the length of the charge distribution, so Q by L. This is the linear charge density of the linear charge distribution, or charge density of a linear charge. Okay, now we have the last phi is equal to Q by epsilon naught, and another phi is equal to E dot S. Okay, now come to this. This S is the Gaussian surface. So now E dot S is equal to Q by epsilon naught. E equal to, what is the Gaussian surface here? The surface of this cylinder around this, in which the flux is flowing. Here, look at this. If you draw a line, field line, it will touches the surface of the cylindrical drawing here, what you drew here. So that means the surface what you have to consider is circular surface. This circular surface area is pi r square L. Pi r square L surface area, which is equal to Q. Q can be taken as pi sigma lambda L by epsilon naught. So L gets cancelled. So E is equal to lambda by pi r square epsilon naught is the field around a line of charge at a distance r. So we have got a field around a linear charge distributions. I am writing here EL is equal to lambda by pi r square epsilon naught. Okay, now come to the surface charge distributions. So for surface charge distributions, here I have a unit volume like this, unit surface area like this. So for this, what is the density of the charge? So here rho is taken as the surface charge density, sorry, sigma. Rho is sigma. Sigma is considered as the surface charge density. Surface charge density Q by, what is the surface area? Okay, here if you take it as a plane, okay, A into B. If you take it as a circle, it is a pi r square. Okay, so just I am writing S, a surface, Q by the surface area. Surface area represented as here S. So Q by S is the surface area whose unit is coulomb per meter square. Okay, so this is called charge density, surface charge density. Sigma is equal to Q by S. Now I will come to the Gaussian surface I need to consider right now. For example, I am considering a plane which is tilted, little bit tilted like this. Okay, so I assume that it is tilted. Now I am considering a unit circular charge here. You have a plane like this and you are considering a circular charge here. So that circular charge, I am drawing a Gaussian surface through which the field lines will flow. So here also the charge, for example, if plane charge exists like this, so field lines will be like this only. It won't coincide with the other lines. So that means the field lines goes in this direction. So that the Gaussian surface assumed is like this. Now come to the point. E dot S is equal to Q by epsilon naught. Okay. So what is S? This is Gaussian surface. Where is the, in this picture, what are the Gaussian surfaces? This is the one Gaussian surface. This is another Gaussian surface. So E is equal to 2 pi r square I am considering. That is equal to, so this is also circle and this is also circle. So for this circle, what is the charge? Sigma into S by epsilon naught. So S is pi r square, only one pi r square, one circular plane you are considering. So it is pi r square. So that is equal to E is equal to sigma by 2 pi r square. So pi r square gets cancelled. Sigma by 2 epsilon naught. For the surface charge distributions, this is the field value, sigma by 2 epsilon naught, where sigma is the charge density of a surface charge distribution. So I am writing here ES is equal to sigma by 2 epsilon naught. One more type of surface charge densities are there. Those are spherical charge surface charge distributions. Spherical surface charge distributions means, for example, you have a sphere. So on that sphere you have charge exists on the top of the sphere. So here also they are occupying some area. So this type of charge distributions we call it as surface charge distributions. Now these this surface charge distributions also field should be like this only. So now we are considering a Gaussian distribution, Gaussian area, like a surface area of this sphere. This is called Gaussian surface area, which is some distance r from the center of that body, So here we will consider, first of all we will consider the charge, surface charge, and we will consider the Gaussian surface. Before that, sigma is equal to, here we are considering only surface charge distribution, so I am finding sigma is equal to q by surface, that is spherical surface. So E dot S is equal to q by epsilon naught is my formula from the Gauss law. So E into S means Gaussian surface. This is the Gaussian surface. I am considering R, and I am considering the sphere's radius as capital R. So now come to this. The Gaussian surface area is 4 pi small r square is equal to Q can be written as sigma S, sigma into the charge surface is 4 pi capital R square by epsilon naught. So here E is equal to 4 pi gets cancelled, sigma by epsilon naught capital R square by small r square is the field on a spherical charge distributions. Okay, so now I am writing that one also. This is outside when you are considering the Gaussian surface outside the charge sphere. If you consider a Gaussian surface inside the charge distributions, so actually what the Gauss law explains, you have to consider the Gaussian surface around the charge. Here you are considering a Gaussian surface around a null charge, so the field will be 0. So that means according to Gauss law, the field inside the spherical charge distribution is 0. One more, physically also I'll demonstrate that one right now. So for example, assume that the charge exists on the sphere. If you write a field line like this, it is going to cross each other. Is any electric field line will cross the